You know, when you watch a rocket launch, you're looking at one of the most powerful and complex things humans have ever created. That incredible fiery tail isn't just smoke and light, it's this roaring river of physics and chemistry. For decades, truly understanding what's going on inside that fire has been a massive challenge in aerospace. Well, today, we're going to dive into how scientists are finally cracking that code. Just look at this. This is not a CGI effect from a movie. This is a real rocket plume, but seen through a special ultraviolet lens. And what just jumps out at you are these beautiful, almost hypnotic repeating patterns, these glowing diamonds of pure energy, just strung together in the exhaust. These right here, these are the clues we've been looking for.
So, what in the world is creating these incredible ghostly shapes? They're often called shock diamonds, and they're basically visible evidence of immense power. They are shock waves that form when the exhaust gas, which is blasting out way, way faster than the speed of sound, slams into the still air around it. They're a vital clue for understanding, and hopefully controlling, the insane forces inside a rocket engine.
And that brings us right to the heart of the problem for aerospace scientists. How do you predict the light, the heat, the entire radiation signature of that plume before you even start building the rocket? And, this isn't just some abstract science project. Being able to predict the plume is absolutely critical. It helps you design more efficient, more stable engines. It's crucial for understanding how all that heat is going to blast the rocket itself and everything on the launch pad. That signature is also how things are tracked in the sky. And maybe most importantly, it's the ultimate test for the complex computer models that all of modern aerospace depends on. The thing is, you obviously can't just walk up and stick a thermometer in a rocket's exhaust. I mean, we're talking about temperatures hitting thousands of degrees, gases moving at supersonic speeds. It is an unbelievably violent and dangerous place. So the question becomes, how do you study something you can't even get close to?
Well, to solve this exact puzzle, a team of scientists in Israel from the Technion, IIRD, and IMI came up with this really brilliant approach. It's kind of like a tale of two plumes. One that was very, very real, and another that was completely virtual. Okay, so here's how they pulled it off. On one hand, they built a real, but much more manageable lab-sized rocket engine. You can see the design for it on the left. They called it the Ballistic Evaluation Motor. And then, on the other hand, they created its digital twin, this powerful computer simulation, which you see on the right, designed to predict all the physics of the plume right from scratch. Now, to make sure the simulation wasn't just guessing, they had to tell it exactly what was burning. The real-world engine used this specific recipe for its solid fuel. It's mostly an oxidizer, ammonium perchlorate, and this kind of rubbery binder called HTPB. These are the key ingredients that create the fire they wanted to predict. So what is this digital twin? It's a hugely sophisticated computer model that uses a technique called computational fluid dynamics, or CFD. Honestly, the best way to think of it is like a weather forecast. But instead of predicting things like wind and rain, it's predicting the temperature, the pressure, and all the chemical reactions happening inside that plume at every single point in space. It's wild. And this is where it all comes to a head, right? They had the real experiment firing in the lab, making actual smoke and fire, and they had the virtual one crunching numbers on a supercomputer. The ultimate test was here. Could the computer's prediction actually match what was happening in the real world? It was time for the showdown, a head-to-head comparison between the photons captured by their instruments and the numbers generated by the code. This was the real world versus the digital twin. Okay, I want you to take a really close look here. One of these images is an actual calibrated photo from the rocket firing in the lab. The other one was created from scratch by a computer. Can you tell which one is the simulation? I mean, look at the patterns, the brightness, the structure. They're just astonishingly similar. So, did you guess? If you thought the bottom image was the simulation, you are absolutely right. And this shows just how incredibly successful their model was. The location of those shock diamonds, their shape, their intensity. The simulation just nailed it. The virtual plume wasn't just some cartoon. It was a genuine reflection of reality. But of course, for scientists, a pretty picture isn't enough. They need the hard data. This graph here plots the brightness of the plume. Those red and blue dotted lines, those are the real measurements from the experiment. And that solid black line that's sitting right on top of them, that's the prediction from the computer model. The takeaway here is undeniable. They match almost perfectly. The simulation didn't just look right, it was mathematically right. Okay, so they proved the model works. Why is that such a big deal?
I mean, it's a monumental achievement, and this is where a really fascinating piece of research starts to revolutionize how we design and build things that fly. Having a digital twin that you can trust is a complete game changer, really for three main reasons. First, it means safer designs. Engineers can test thousands of virtual rocket ideas on a computer without the enormous risk of a real-world test. Second, it is so much faster. A simulation can run in a few hours, but building and testing new hardware, that can take months, even years. And third, it is way, way cheaper. It just slashes the cost of materials, fuel, and all the test facilities. You know, in that classic, understated language of science, the researchers summed it all up perfectly right in their paper. These simulated and experimental results agree well in the measured region. That one simple sentence represents a massive leap forward in our ability to engineer some of humanity's most powerful technology. And that really leaves us with this final, powerful thought. If we can now accurately simulate something as chaotic, as hot, and as ridiculously complex as a rocket's fire, what's the next impossible thing we'll be able to predict and design and perfect all inside a virtual world?